So far, the kinetic energy we've been talking about is what we call linear kinetic energy. Motion in a straight line, there's no rotation. And remember, that kinetic energy is 1/2 mv squared. V is the linear velocity, velocity in a straight line. But we also have a rotational analog to kinetic energy. We have rotational kinetic energy. So the rotational kinetic energy is 1/2 times the moment of inertia times the angular speed squared. So it looks really similar. We still have a 1/2, and instead of a mass, we've got the moment of inertia. And instead of the linear speed squared, we've got the angular speed squared. Angular speed here will always be in units of radians per second. So where does this equation for rotational kinetic energy come from? Well, imagine we have an object in the shape of a thin, rigid plate, unusually shaped here, rotating around an axis perpendicular to its plane. So here we've got our unusually shaped object. It's rotating with an angular speed around an axis perpendicular to it, okay? And our plate consists of many small particles of mass. So I'm just going to draw one in right here. That's a small particle of mass. Now, all particles are going to rotate in a circular path around the center, okay? And it will rotate with a linear speed equal to its angular speed times r, the distance away from the center of rotation. And we've already seen this equation before when we're talking about rotational motion, okay? So the total kinetic energy, and this distance is r, the total kinetic energy of this plate is the sum of all the kinetic energies associated with each particle. So that means that our total rotational kinetic energy for this unusually shaped object is going to equal the sum of the kinetic energy 1/2 mv squared of all those little particles that are moving around on the plate as we're executing rotational motion. So we can always bring this 1/2 out of the summation sign. So this is equal to 1/2 times the sum of mv squared. So remember, v is equal to omega r. So this is equal to 1/2 times the sum of my masses times omega r and that whole thing squared. Okay, so this is equal to 1/2 sum m omega squared r squared. Now every single particle on this object, as this object is rotating around the central rotational axis, every one of those objects has the same omega. Because remember, omega is equal to your change in angle over change in time. So no matter where you are on this piece, wherever you are, your angular distance that you move through in the same period of time is the same for every single particle. So omega is the same for every little mass point on this shape. So if omega is the same, that means that I can pull omega out of the summation sign because it's going to be the same for every particle. So this is equal to 1/2 omega squared times the sum of m r squared. And remember that this, the sum of m r squared, is the same thing as the moment of inertia of a body. The moment of inertia of any object is the sum of all the individual mass particles it's made of times the distance that those mass particles are away from the rotational center squared. And so that's how we get our equation for rotational kinetic energy, 1/2 times the moment of inertia omega squared. And we just derived that from our original equation for linear kinetic energy, and just using the fact that linear velocity is equal to omega times r, and that omega is the same for every one of those particles. So conservation of energy still applies even in a rotating system. So imagine you have a ball that's rolling down an incline, okay? It has this linear kinetic energy, which sometimes you'll see it as sub T for translational kinetic energy. It's the same thing, 1/2 mv squared. V is our linear speed. Plus now a rotational kinetic energy because our object is going to be rotating, which is 1/2 moment of inertia omega squared, plus the initial gravitational potential energy. And then that has to equal at some later time the final linear kinetic energy plus the final rotational kinetic energy plus the final gravitational potential energy. And this also applies to our work kinetic energy theorem. We said that our work that we do in the system is equal to the change in kinetic energy plus the change in potential energy, and in this case also plus our change in rotational kinetic energy. And we're also going to apply our work kinetic energy theorem here too. So there is net work done in a rotating system if you have some force that's applied and you're moving through some arc length. So we're going to apply our conservation of energy, linear kinetic energy, rotational kinetic energy, and gravitational potential energy in order to solve a problem where we have a ball rolling down an incline.
So we are going to think about the difference between a problem when we don't have rotational kinetic energy and a problem when we do have rotational kinetic energy. And a really great example is thinking about the Galileo lab that we did way at the beginning of the semester, for those of you in my lab course. So we had a marble that we started at the top of an incline and we let it fall to the bottom of the incline, and then when it reached the bottom of the incline, it launched off the end of a table and executed projectile motion to the ground. Okay, and we were interested partly in finding what was the velocity of that ball when it reached the bottom of the incline. And back then, we only knew about kinematics. So we had to solve that problem for the velocity of the ball at the bottom of my incline here using kinematics. And I'm not going to walk through that entire problem again, but if you look back at the notes, if you look back at that video that we walked through, the velocity at the bottom of the incline here, we wrote that as V parallel equals G sine theta times T, okay? T was the time it took to roll down this plane, and that time we found was G sine theta. That time that we found was the square root of 2 times D parallel, which is the distance it rolls down the incline, divided by A parallel, which was our acceleration along the incline. And we also found that A parallel was equal to acceleration due to gravity sine theta. Okay, so I'm not going to walk us through how we found those. But if I plug that into this equation, we found that the velocity of the ball when it reaches the bottom of this incline, which I'm calling V parallel, was G sine theta times the square root of 2 times D parallel divided by this acceleration, G sine theta. Okay, now I want to put everything inside the square root sign for a reason we're going to see here in a minute. This is all under a square root sign. So I can always write G sine theta as G sine theta squared and take the square root of all of that, because when you take the square root of something that's squared, you get that number back again. Then we're going to multiply it by the square root of 2 times our distance parallel, that's this here along the incline, divided by G sine theta. Okay, and so then I can put this number that's square rooted inside this equation. And so then this is equal to the square root of G sine theta squared times 2 D parallel, all divided by G sine theta. So this G sine theta on the bottom cancels with one of these G sine thetas on the top. So then our parallel velocity, or the velocity that our ball has when it reaches down the bottom of this plane here, is equal to the square root of D parallel G sine theta. Okay? And you can go back and double check. All right. And if we say that the distance that we're rolling down this incline is 10 centimeters, or 0.1 meters, and this angle here of my incline is 20 degrees, then when I plug that in here, 2 times 0.1 meters times G sine of 20, take the square root of that, we get that that velocity that we have at the bottom of the incline was 0.819 meters per second. And you had to find this value for one of the quantities I asked you for that lab report for that Galileo lab, okay? Now, I'm going to show you how we can get this exact same equation and that exact same number using conservation of energy. And then you might be a little bit mad at me because the conservation of energy way is much simpler than this. Okay, so if we do it with conservation of energy, we want to find the speed of our ball at the bottom of the incline. If it's starting from rest up here, then we say that the kinetic energy of the ball at the top of the ramp plus the potential energy of the ball at the top of the ramp equals its kinetic energy at the bottom plus its potential energy at the bottom of the ramp. Okay, now when we reach the bottom of the ramp, we don't have any gravitational potential energy anymore. Height is 0 here. When we're at the top of the ramp, starting from rest, our initial kinetic energy is 0. So then we have our gravitational potential energy is mass times gravity times height. So we have mgh equals 1/2 mv squared, because kinetic energy is 1/2 mv squared. This velocity is going to be what we're calling v parallel. That's the velocity of our ball when it reaches the bottom of the ramp. Now the masses cancel on both sides. I'm going to solve this for v parallel again. So if I'm divided by 2, I can multiply both sides by 2 to get rid of this half on this side. So 2gh equals v parallel squared. So square root both sides. V parallel is equal to the square root of 2 times g times h, our height above someplace where we're saying y is equal to 0. Now, I can put this h in terms of my angle theta and my distance down the incline. So I can do that by using trigonometry. So I can say that sine of my angle theta here is equal to opposite, which is h, over the hypotenuse, which is this distance we're calling d parallel, the distance we roll down the incline. So h is equal to d parallel sine theta. So I can replace this h here with 2g times d parallel sine theta. And so this velocity is exactly the same as what we found right here when we were using our kinematic approach way back at the beginning of the semester. Now we saw using this approach to get our velocity for the ball at the bottom of the ramp, which went into our equation for range, that a lot of us, or most all of us, found a range in the experiment that was much shorter than the range that we calculated. That's because the range that we calculated depended on this velocity that we found for the velocity of our ball at the bottom of the incline. And we took that, to get that equation, to find that velocity, we had to use kinematics. We also could find that same equation here we saw by using conservation of energy. But this is not taking into account the fact that our ball actually rolls. Okay, using this approach right here and here, we're just thinking about that ball just sliding down, just translating down the plane. But we know that it's rolling as it does this in reality, okay? So there's a kinetic energy associated with rotational motion, which doesn't get taken into account in this approach right here. So when we take the rotational kinetic energy into account, as our ball is rolling down the incline, not just sliding down the incline, that changes our velocity at the bottom of the incline, actually reduces the velocity at the bottom of the incline. So that's why our values that we found for the range were overestimates of what we actually found when we did the experiment, because we were overestimating this quantity for the velocity of our ball at the bottom of the ramp. So let's find what the velocity of the ball at the bottom of the ramp should have been whenever we take into account rotational kinetic energy. So we can still use this, but now this time we have to take into account rotational kinetic energy. So we've got our initial kinetic energy plus our initial rotational kinetic energy plus our initial gravitational potential energy equals our final kinetic energy plus our final rotational kinetic energy plus our final gravitational potential energy. So our final gravitational potential energy will be 0 when we're at the bottom of the ramp. Our initial kinetic energies, both the regular one, the translational kinetic energy, and the rotational kinetic energy are 0 if we're starting from rest. So we've got our gravitational potential energy at the top of the incline has to equal not just the translational kinetic energy at the bottom of the incline, but translational kinetic energy plus rotational kinetic energy. So some of that initial potential energy has to convert to rotational kinetic energy and translational kinetic energy. Okay, so if we've got mgh equals 1/2 mv squared, that's our v parallel, plus our rotational kinetic energy is 1/2 times the moment of inertia of our object times omega squared. Now we know that we can rewrite angular velocity as omega equals our translational velocity divided by the radius of the object, or the radius of the circle around which we're moving, circular path around which we're moving. For this marble that we're going to roll down the plane, let's assume that that moment of inertia is the moment of inertia of a solid sphere rotating around its center. And that moment of inertia is 2/5 times its mass times its radius squared. Then we can write this as mgh equals 1/2 mv parallel squared plus 1/2 times our moment of inertia times, we said that omega we can write as v over r. So v over r, that whole thing squared. Write this like this, 1/2 m v parallel squared plus 1/2 I, we've got now v squared over r squared. And this is also our parallel velocity, okay, our velocity that we're going to have at the bottom of the ramp here. So we can factor out a 1/2 v parallel from this side. This is 1/2 v parallel squared times mass plus moment of inertia divided by r squared. All right, so let's plug in what we have for our moment of inertia. So we've got mgh equals 1/2 v parallel squared times mass plus 2/5 mr squared over r squared. Okay, so our radius cancels on top and bottom. So in here, we've got m plus 2/5 m. Okay, how can we write that? Well, you could add 1 plus 2/5, okay, but and get it as a decimal in your calculator. But let's do it like this. I'm going to use it in pink so we don't get it mixed up with what we're doing elsewhere. So you can always write this quantity m as, let's see, so we've got m plus 2/5 m. Okay, we can write m as 5 over 5 times m plus 2/5 m, because when we add fractions, we want to add fractions that have the same denominator on the bottom. So we've got 5 over 5 m plus 2 over 5 m's. We add the top numbers, the numerator, but you keep the denominator the same whenever you're adding fractions. So then this 5 over 5 m is 1 m plus 2/5 m. This is the same thing as 7/5 m. Okay, so this whole thing, m plus 2/5 m, is the same thing as 7/5 m. So then this is equal to mgh equals 1/2 v parallel squared times 7/5 m. And my m cancels on both sides. If I take 1/2 times 7/5, that's 7/10 v parallel squared. Now I solve this for v parallel squared. V parallel squared equals 10 over 7 times gh. Now if I square root both sides here, then I get that v parallel is equal to the square root of 10 over 7 times g times h. And we found an expression for h earlier. That's the same thing as d parallel sine theta. Okay, so now we've got this equation for v parallel that looks similar to this other equation that we found for v parallel when we weren't taking into account rotational kinetic energy. So 10 over 7 is smaller than 2. So that means that this quantity down here for v parallel is going to be smaller when we take into account rotational kinetic energy. So really, we were overestimating the velocity that our marble had at the bottom of the incline, which is why we were overestimating the range for our experiment. So in this case, v parallel should have been 0.69 meters per second if we were using a distance rolling down the plane of 10 centimeters and also an angle here of 20 degrees. Okay? So I wanted you to see the difference that happens whenever we take into account rotational kinetic energy. All of that initial potential energy doesn't get converted down here at the bottom of the ramp to just kinetic energy. It has to be converted into both kinetic energy and rotational kinetic energy. So that rotational kinetic energy is sort of stealing some of that energy that could have gone into the translational kinetic energy. And so that means whenever you reach the bottom of the incline, that really, in actuality, that velocity that our ball had at the bottom of the incline was a little bit less than what we had initially calculated.
For this engagement check question, I'm going to ask you to think about rotational energy. We're going to have two objects with the same mass and radius, and they are rotating with the same angular speed through an axis through their centers. Which one has the highest rotational kinetic energy? Is it a solid sphere or a hollow sphere? Well, think about the equation for rotational kinetic energy. What is it? I'm saying that omega is the same for both of these objects. The masses are the same, the radius are the same, but each of these objects is going to have a different moment of inertia. So, which of these two objects is going to have the largest rotational kinetic energy? A solid sphere or a hollow sphere? And to solve that, you're going to have to know what is the moment of inertia of each of these objects. So down here I have the moment of inertia for a solid sphere around any diameter, and here I have the moment of inertia for a thin shell about any diameter. So imagine a hollow sphere. And so their moment of inertias are different, and you're going to take that into account when you think about which has the highest rotational kinetic energy. Is it going to be your solid sphere or your hollow sphere? And then after that, I'm not going to ask you to do number 3, but number 2. Which of these two objects then are going to arrive at the bottom of a frictionless incline first? Is it going to be our solid sphere or is it going to be our hollow sphere? Okay, so in order to think about that, you don't necessarily have to solve the problem, okay? But you can think about this. They start with a gravitational potential energy, the same for both of them at the top of the incline. Okay, then they're going to roll down and then they're going to reach the bottom of the incline. So they're going to convert that gravitational potential energy into linear kinetic energy and rotational kinetic energy. Okay, so which one arrives at the bottom of the incline first? That's going to be the one that's going to have the largest linear velocity v. Okay, and so you're going to have to think about, as those objects are rolling down the incline, which one's going to have the largest rotational kinetic energy? Because we have to take the gravitational potential energy, that has to equal your rotational kinetic energy plus your translational kinetic energy. So the one that has the largest rotational kinetic energy is going to steal some of that energy away, some of that available energy away from the translational kinetic energy that gives you the linear speed at which you're going to end up at the bottom of the incline. So the one that reaches the bottom of the incline first is going to be the one that has the smallest rotational kinetic energy. The one that takes the longer time to reach the bottom of the incline is going to be the one that has the largest rotational kinetic energy.